Hi, this is Supratim. I am excited to be your guide in this tutorial video, Magnetocaloric version 0.3.0, a standalone software designed for the convenience to study the magnetocaloric performance as well as the magnetic property from any sample image data. In this video, I explore the interface to demonstrate the fundamental features and how to effectively utilize this tool. This software is built upon the Python module magnetocaloric.mcepy. To enhance the user experience, I crafted the user-friendly graphical interface using PyQt5, transforming it into a standalone executable file for your ease of use. This video, I will delve into the fundamental functions of this magnetocaloric 0.3.0. While we can't cover everything due to the time constraint, but this overview will give you the solid foundation. Our demonstration employs the sample data of GD1, the courtesy of the authors and co-authors of the article titled Tunable Magnetocaloric Effect in GD-based class ED1. Their generosity allows me to show the data in my project report. Now let's explore the data formatting requirement of this software. Just take a look at the screenshot of the source file. Vertically, we have the applied magnetic field value and horizontally the corresponding temperature values with their magnetic moment. This precise arrangement is crucial for loading data. You may notice that this is the sole file in this current folder. However, if you enable the obtain data save option from the GUI, the calculated data in XLSX format will be automatically stored in an output folder in this directory. And further, we can check it after performing the calculation. Suppose you wish to plot the entropy change versus temperature and want to save the obtained data into the blank XLSX file. Then what is the process? This is the step-by-step demonstration. Will show you exactly how to achieve this, ensuring you that you have both the plot you desire and the data saved for future reference. First, you got to select the file directory. Here you have two options: navigate through the file explorer, and also you can simply copy and paste the directory directly, whichever suit your preference. Here I am using file explorer to select the source file. And after selecting the source file, I am setting this directory. And once the directory is set, it is important to specify the seat index which the actual image data resides. Here, in my cases, the data resides in the seat number 1. So that's why I am putting 1. And then fine tune your data configuration by selecting the appropriate temperature row and magnetic field column using the slider. Here, the magnetic field data column is A and the temperature row is 1. You can check here from this spreadsheet that the temperatures are in row 1 and the applied fields are the column A. And don't forget to keep an eye on the execution log. It's here that you can cross check the value you have assigned to ensure everything is set up correctly. Now it's the time to enter the sample name and specify the units. Here the sample name is GD and the magnetic moment we have in EMU per gram, and the applied fields are in Oersted, temperatures are in Kelvin. Here we can see that the sample name, magnetization unit, and magnetic field unit, temperature units are assigned with their specific values. Now the heart of the operation lies in the function selection. You have three options in this function. The number one is interpolation, second is 2D plot, third is 3D plot. Here in this scenario, our goal is to create 2D plot of entropy change. Hence, I am selecting the 2D plot function and launching this function. After selecting this function, you will find the available plots listed in this graph name. From here, you can choose the desired plot using the combo box. Here, the available plots are MH, MT, entropy change plot, mean field error plot, modified error plot including Ising model, Heisenberg model, susceptibility plot, and relative cooling power plot. And in this demonstration, we are focusing on the entropy change plot. Then that's why I am selecting the entropy change. To enhance the clarity, we are enabling the graph legend with the best position. And don't forget to active the data saving option if you want to save the data. With everything set up, it is time to hit the execution button and see the entropy change plot came to life. Here we can see the entropy change versus temperature plots. The each and every lines represent the specific applied fields. Similarly, here we can see the other plots. If you want to see the M versus T plot, then set the plot name empty plot, then execute. But this is the M versus T plot. This is MH. This is main field arrow plot, and these are the modified arrow plot. This is the RCB plot. And if you just want to plot the susceptibility and inverse susceptibility, just set the default magnetic field at which you want to plot here, and you gotta put the exact value of the seat you have. Here I want to plot the susceptibility at that field. That's why I am copying this value and pasting it. And if you don't want to see the linear fit of Fourier's temperature, just enter the threshold value 0. Yes. Here we can see the inverse susceptibility and susceptibility versus temperature. Here we can type the layout for better view. Similarly, if you want to see the 3D plots, then we have to launch the function the MC3D plot, and now you can see the available graphs name. Suppose we want to see the M distribution. Here, this is the image distribution plane in 3D view. You can see the M versus T graph, and here you can see the M versus H, and also you can plot the DMDT 3D plots. This is the DMDT 3D plot, and this is the DMDH 3D plot, and this is the entropy change distribution. By default, it selected the value of DPI in 1600, but you can adjust the DPI by giving the specific value. Now delve into the interpolation of magnetic moment concerning the applied field. It is essential to remember that the interpolated data will override the existing data in the source file. Please exercise the caution when using this function. Here I will demonstrate the fitting of polynomial curve within a specific range. Initially, I have set the degree in 2 and the range will be initial field value is 500 and interval will be also 500 and the final field will be 50,000 posted. And I am interpolating manually. That's why I set the interpolation manual, and this I am going to fit polynomially. Now you can see the square error approach the value of 0.030, which is significantly quite large. To minimize the square error, you can change the degree. Now I have adjusted it to 3. As you can see from this curve, the error is significantly minimized. And enabling the auto, it will attempt to find the best fit automatically. Here you can see the maximum error is 0.0008, which is very small. And that concludes our tutorial on Magnetocaloric 0.3.0. I hope this has been a valuable guide to using this software effectively. Stay tuned for more in-depth tutorial and don't forget to like, share and subscribe for future updates. Happy exploring and until next time, keep innovating.